The hypothesis of an ancient astronomical explosion proposes that the universe started from nothing, suggesting that before the colossal blast, there was nothing, no time, no space. Yet, think about how conceivable it is that I let you realize that time is a double dealing and that the huge explosion speculation may be misguided. New revelations from the James Webb Space Telescope are examining the accuracy of this speculation. The colossal blast presumably won't really take a look at the start of the universe. Taking everything into account, there's a believability that time is merely a misdirection. This idea finds support from respected English physicist Roger Penrose. You might be curious about how the James Webb Space Telescope maintains time being a misdirection. Furthermore, if the colossal bang theory isn't exact, what other speculations have been proposed to describe how the universe began and made? We ought to dive in to sort out the possibility that our universe started expanding 13.8 billion years ago in a fixed state called the hypothesis of how things came to be. This hypothesis has encountered obstacles, especially with ongoing pictures from the James Webb Space Telescope. While these photos are enchanting to the layman, they have caused stress among cosmologists and astronomers. The surprise felt by experts comes from the way that these photos conflict with the hypothesis of how things came to have a place, maintained as substantial by various specialists. The new data has caused an immense aggravation in established analysts. Astronomers like Alison Kirkpatrick from the University of Kansas lament this development, tending to the authenticity of their past understanding. The problem lies in the characteristics of the universes depicted in the JWST pictures. These universes appear small, smooth, and remarkably old, as shown by the hypothesis of the universe's starting point. As space develops, systems and various objects should appear greater as they move away from us due to the stretching of light. However, the JWST pictures show that the systems turn out to be more unobtrusive as the distance increases, which conflicts with the theory. Even vast systems with more unmistakable mass and brightness than our own appear to be a couple of times more unobtrusive in the JWST pictures compared to past observations by the Hubble Space Telescope. Additionally, the redshifts found in these universes are a few times more noticeable, further testing the assumptions of a developing universe in the gigantic bang theory. These realities suggest that faraway universes ought to be extremely microscopic to account for this optical trickery, which is impossible. The presence of these small and smooth universes attacks the possibility of evolution, further extending vulnerability on the hypothesis of the universe's starting point. Proponents of the ancient Big Bang theory realize that their assumptions gain the presence of these small and dense systems, often referred to as strong mouse grandiose systems, based on past insights from the Hubble Space Telescope. At any rate, the JWST pictures have complicated the situation by discrediting the chance that these tiny universes could form into greater frameworks through accidents or augmentation. The JWST pictures show well-defined spiral galaxies and smooth disks, similar to the grandiose frameworks we notice today. This goes against the presumption for damaged and curved infinite frameworks occurring as a result of accidents without immense unions. The infinitesimal grandiose frameworks can't become multiple times greater, showing that they were not at first minimal. This finding challenges the optical trickiness expected by the developing universe theory, suggesting that there is no development and hence no gigantic bang. Furthermore, the age and abundance of universes in the JWST pictures also present problems for the hypothesis of the universe's starting point. By using infrared channels, the JWST can capture the colors of faraway vast frameworks, allowing cosmologists to assess the age of the stars within them. According to the speculation, these far-off universes should represent a period around 400 to 500 million years after the Big Bang. However, a number of these frameworks show significant masses that are over a billion years old, conflicting with the assumption that nothing could have existed before the colossal blast. Researchers had guessed that as the JWST looked further into space and farther back in time, there would be fewer systems and eventually no faint age. Yet the pictures reveal systems as broad as the Smooth Way, even a couple 100 million years after the visitor Big Bang. Moreover, the quantity of systems observed at redshifts greater than 10 is at least multiple times more noticeable than expected by researchers. It is dicey for so many large universes to form in such a short period, testing the hypothesis of an ancient Big Bang. These revelations have prompted the examination of time itself. A couple of scientists argue that time is simply a human construct and a way to differentiate between the present and our impression of the past. They suggest that time is a duplicity created by human memories, proposing that all that has ever happened or will ever happen is occurring at the same time. This perspective challenges the notion that time must move strictly in a forward direction. The idea of the Big Crunch theory even suggests that when the universe stops expanding and begins contracting, time might reverse, provoking a return to the cooling and evolution found in the Big Bang. Ultimately, the consequences of what comes after a significant crunch remain uncertain, with various speculations proposed. Some estimate that the universe could undergo another start with another gigantic bang, while others suggest it may simply stop to exist. Specific considerations propose a cyclical nature, with the universe reiterating various events and creating different universes. This continuous discussion about the direction of time has incited investigation into its fundamental nature. Some advocate for a block universe theory, where the truths are interconnected in what is referred to as spacetime. According to a speculation maintained by Albert Einstein's theory of relativity, events are significant in a four-dimensional structure, where each event has what is known as a punctuated existence. Spacetime derives that everything, counting the past and future, exists together in spacetime, making them correspondingly gigantic nearby the present. Physicist Max Tarr from the Massachusetts Association of Development addresses this thought. He suggests that reality could be depicted as either a three-dimensional space where circumstance fosters over an extended time or a four-dimensional space where nothing changes. It is certified then to expect the latter choice. It derives that everything at this point exists all of a sudden, wrapping the past, present, and future. At any rate, we have a misdirection that the past has occurred and what's in store is on the way, leading us to see change. Julian Barber, an English physicist who has elucidated extensively on time, offers his perspective on this matter. He portrays our experiences as a movement of nows and calls attention to the fact that we are, figuratively speaking, aware of our frontal cortex. Our wisdom of the past arises out of our psyche taking care of memory. Barber escapes to the spacetime theory, where each point in this applied country, which he calls Plutonia, tends to a now. He suggests that what we acknowledge as the past is simply a trickery made by our frontal cortexes. This discussion returns us to Albert Einstein's speculation of spacetime, which has caused some chaos in the field of material science. Scientists are now pondering what may happen if Einstein's speculation were proved mistaken. Would discarding the theory of spacetime help us with procuring a better understanding of the universe? This would be an immense development over the whole process of everything working out. Intelligent revolts have been critical for progress. Disillusionment and inquiries in the end lead to the ascent of new hypotheses that override the old ones. This paradigm shift has happened multiple times in the fields of room science and actual science. At first, mankind accepted that Earth was at the central place of the planetary gathering, a conviction that persevered for over 1,000 years. However, Nicholas Copernicus proposed a substitute theory, suggesting that it would be less challenging to consider Earth as just another planet circumnavigating the Sun, not enduring starting hindrance. This heliocentric model garnered support with the advent of telescopes. Isaac Newton also contributed to our understanding by grasping that the gravitational force of the Sun makes planets circle it, as demonstrated by Newton. Objects with mass apply gravitational attraction on one another, which explains Earth's orbit around the Sun and the Moon's orbit around the Earth. Newton's speculation managed consistent thought for nearly 300 years until Albert Einstein introduced his general theory of relativity in 1915. This new theory addressed anomalies in the orbit of Mercury and was extensively confirmed during a solar eclipse observation in 1919 off the coast of Africa. Instead of Newton's idea of gravity as a pull, Einstein envisioned gravity as a curvature of space. He proposed that all objects in the universe exist within a four-dimensional surface known as spacetime. Massive objects like the Sun bend this surface, causing planets to follow these curves and stream in their orbits. To observers, this bend appears as Newtonian gravitational pull. Einstein's theory of spacetime has ruled for more than 100 years, obscuring competing hypotheses. The discovery of gravitational waves in 2015 further cemented its significance. However, like its predecessors, it may soon face challenges as it clashes with another prominent theory in actual science, quantum theory. The quantum world is known for its characteristics, where particles can exist in various states at the same time. During the 1930s, Erwin Schrödinger extensively described the peculiar concept of quantum superposition with his Schrödinger's cat thought experiment. It involved a sealed box containing a vial of poison connected to a hammer triggered by a quantum event. According to quantum physics, until the measurement is made, the particle exists in a superposition of both states, leading to the paradoxical situation where the cat is simultaneously alive and dead. However, this picture of quantum superposition cannot be reconciled with the consistent and smooth surface of spacetime. Even Sabine Hossenfelder, a theoretical physicist at the Frankfurt Institute for Advanced Studies, perceives this dispute. According to Einstein's theory of spacetime, a gravitational field can't be in two states simultaneously. It's influenced by mass and energy and is, nonetheless, dependent on curvature. Quantum physics suggests that matter and energy can exist in various states simultaneously, challenging traditional notions of locality. This raises the question, where does the gravitational field abide? Hossenfelder contends that there's no adequate answer to this question, highlighting the current challenge in reconciling general relativity with quantum theory. Tries are made to mix these two. Speculations and mathematical inconsistencies arise. Assessments, a portion of the time, yield probabilities more uncommon than 1 or even infinity, which have no critical real interpretations. Thus, the two speculations are numerically incompatible. Physicists, much like credible rulers searching for alliances, are currently searching for a united theory of quantum gravity. This attempt aims to reconcile the two rival hypotheses and establish compatibility between them. String theory is perhaps one of the most notable proposals in this endeavor. Often considered an astonishing possibility, string theory suggests that tiny vibrating strings make up subatomic particles like electrons and quarks, just as different notes can be produced by plucking strings on an instrument. String theorists argue that various combinations of strings create distinct particles. This theory is captivating because it may potentially reconcile general relativity with quantum mechanics. However, for this theory to work, the strings must vibrate across 11 dimensions, which is 7 more than the 4 dimensions in Einstein's spacetime framework. Currently, there is no experimental evidence to support the existence of these additional dimensions. While it is an intriguing mathematical idea, we can't be sure it accurately describes the spacetime in which we live without driving experiments. According to Joanna, a researcher at the University of Nottingham, considering the evident shortcomings of string theory, physicists have turned to an alternative approach called loop quantum gravity, LQG. With LQG, the two theories can be reconciled by questioning one of the fundamental principles of general relativity, which asserts that spacetime is a smooth continuum. Rather, LQG suggests that spacetime contains interlaced loops, giving rise to a structure at the smallest scale. This can be compared to a surface that appears smooth at a glance, yet reveals a network of lines when examined more closely. It is similar to a photograph on a computer screen that appears clear until zoomed in. The challenge with LQG is that when physicists refer to something as small, they mean it is incredibly minute. These flaws in spacetime would only be observable at the Planck scale, which is around a trillionth of a trillionth of a trillionth of a meter. The number of loops in a cubic centimeter of space would exceed the number of cubic centimeters in the entire observable universe, as demonstrated by estimates. If spacetime fluctuations are limited to the Planck scale, testing this sounds daunting. It would require a particle collider approximately 1,000 trillion times more powerful than the Large Hadron Collider, LHC, at CERN, which would need to be nearly as large as our entire observable universe. Nonetheless, a group of physicists from the UK, France, and Hong Kong may soon have an alternative method to test this idea. They hope to utilize an ultra-cold gas containing billions of cesium atoms existing in a state known as a Bose-Einstein condensate to investigate whether gravity exhibits quantum properties. In the meantime, the actual universe offers another venue to search for small spacetime fluctuations. Light that reaches us from distant parts of the universe has traversed billions of light-years of spacetime. Although the effect of each spacetime deformation would be negligible, interactions with multiple deformations could accumulate and possibly yield observable effects over such vast distances. Astronomers have been sifting through light from far-off galaxies over the last decade to search for evidence supporting loop quantum gravity.